let's start talking about microbial stabilization during aging. The first thing is that I want to talk about is why are we talking about this? So the thing is, if there is a microbial contamination on wine, it can be actually a massive impact in terms of wine quality, but also wine quantities and also economic. A microbial contamination can be very quickly large, not under control. The impact of a deviation is irreversible. So even if we have a treatment to help the wine properties after a contamination, it will never get to the quality that it was before. So it is irreversible. It is fast, and as I say, there is a pretty big economic impact associated to it, because you lose wine. You have a lot of treatments to do, which are usually having a cost, and also you lose quality, so you will never sell the wine for the same price. So who are the responsible? The microbes that we're talking about or focusing on during aging are mostly Acetobacter, Lactobacillus, Pediococcus, and Brettanomyces. These are the 4 big families of microbes that are at big risk during aging. If we put them in conditions, in favorable conditions, with growth promoters such as sugar, malic acid, citric acid, assimilable nitrogen, but also dissolved oxygen, or a higher temperature they like, that's where we face the risk of having consequences. We face the risk of developing acetic acid, ethyl acetate, acetaldehydes, volatile phenols, such as also bread taint, lactic taint, and also biogenic amines. These are the main the main fault, I would say, that we can find into wine during aging. They are not the only one, of course, but they are the main one. Okay, so we want to avoid this. We want to avoid to do treatments to the wine and have high economic impact. So to really have the wine under control during aging and actually just take it easy a little bit during the holidays and have some time to rest after harvest, we are gonna talk about prevention. So the program of today is really about focusing on preventive approach. It's always better to prevent than cure, and always easier. The first point we will talk about is about cellar and wine conditions. So talking about barrel management, using a steamer, using ozone, cleaning, hygiene is very important. I'm not talking about making the winery an hospital. I'm just talking about having a minimum of hygiene and sanitation procedures. We'll talk about fining, how to lower redox potential and also limit dissolved oxygen, because these are very important factors to control and manage microbial population. The second point, of course, which antimicrobial agents we can use and how to use them, what is available to us, a winemaker, during aging. And then I would like to talk a little bit about how to prevent the spoilage of the wine. So sometimes we can have the microbes, but we have for 2 wines that are different, but same amount of microbes, the spoilage is not going to be the same. The impact on the wine is not going to be the same. And this is mostly due to how much substrate we have into the wine. So there is just some practices to adapt that we can, where we can limit the substrate and so limit the spoilage. Okay, so let's start with the first point, cellar and wine conditions. As I told you, rigorous hygiene and sanitation are essential. Using a steamer when you are handling barrels, steamer, ozone are very important. Using, there is many ways to clean and sanitize tanks, but for barrels, usually it's steam or ozone or both. But make sure you have a good procedure that is completely verified, and then you apply it all the time. Lower temperature, so it's always good to work at lower temperature during aging. So the cellar needs to be at lower temperature. The wine managing pH is probably the best tool you have to control microbes. Of course, it's changing the organoleptic parameters, but it is essential to control pH as well. So the lower the pH, the less risk you will have. Lower turbidity, we saw, and we're going to see just later, that racking and fining can really help lowering the overall population of microbes. The microbes live in the lees, and so if you want to avoid contamination, it's good to remove some of the lees. The heavy lees and reducing turbidity can be essential practices in help in managing microbes. Reducing dissolved oxygen. Oxygen is a nutrient for microbes in general. So most of the microbes we talked about and that are present in wine during aging are actually loving aerobic conditions. So if we reduce dissolved oxygen, we will put them in not favorable condition, and so we can control them better. For this, of course, good cellar practices, make sure you, if you do a transfer or racking, make sure you control it and you use inert gas. Make sure you top your wine regularly, but also the use of tannins and glutathione can be great tools to scavenge oxygen radicals and to limit dissolved oxygen. Lowering redox potential is also great. These microbes don't like to live in low redox potential, but they do like high redox potential. So the lower you are and the more stable you will be in terms of microbial. So you can use glutathione and you can use tannins. Sulfur works too. But glutathiones and tannins are great tool to really put your redox potential lower and more stable through time, which will help you to manage microbes. So we're going to focus a little bit more on these three last point that I just talked about. First one, fining. So as you can see here, just a regular fining followed by a racking will help to reduce the population of microbes. In this case, Brettanomyces. So here we are having two petri dish where you can see the wine before fining has been showing 31,000 colonies per milliliter of Brettanomyces in this case. And we did here a small fining of gelatin. It could be any fining agent that will help clarifying the wine and reducing turbidity. It just binds the microbes and put them into the lees. So when you do the racking, you have less microbes in suspension. But as you can see, it's not just a little bit less, it really helps. We went from 31,000 colonies per milliliter to 180 with a fining agent that is not specific to microbial control. So a fining is going to help reducing the microbial overall load in the wine, but it also will help you to have a better efficiency of your antimicrobial treatment, so you can use it at lower dosage. So it's a very interesting and pretty easy tool. Fining, clarification, followed by racking. It's really about racking of lees. Then we talked about lowering redox potential and limiting dissolved oxygen. So here I'm gonna go fast on something that is a little bit complex, so stay with me on this one. We know that tannins have a great, they have a very low redox potential and they are great affinity with radical of oxygen. So we are looking at the oxygen consumption rate of different tannins to understand which one we can propose and which one we should be using in winemaking. So this is a study of Vigno in 2018, where they looked at different type of tannins and their oxygen rate, their oxygen consumption rate. And we can see here that the oak is the one that consumed the fastest. So we understand that oak tannins are better to consume oxygen. Okay. We also know that oak tannins are the best in terms of buffering redox potential. So buffering redox potential means we are looking at the wine redox potential, and we are, when we add oak tannins, or when there is wine into barrels, so there is more oak tannins into the wine will have less sensibility to fall into reduction or oxidation. It has more protection and a buffer, a stabilization of the redox potential. So looking at this study, we did the same at La Motabier with our own product, and we found, not surprisingly, but we found the same results. We found that our oak tannins are the one that consume the oxygen the fastest. Okay, so we have tannessence forte and tannessence volume that are our oak tannins that are the most performant in oxygen consumption rates. And then we have our skin tannin that is way less, and our gallic tannin that is way less, exactly the same order than the study that I talked about previously. From this study, we concluded that, and we recommend to people to add at any racking, any transfer, or any movement of the wine, we recommend to use 0.5 to 1 gram per hectoliter of tannessence volume. Why tannessence volume and not tannessence forte, which is more efficient in oxygen consumption rate? It's because tannessence forte has a stronger organoleptic impact. And so the goal here is really to focus on stabilizing redox potential, catching the oxygen radicals to limit dissolved oxygen, and to reduce the potential nutrients for microbes. And so not to change the aromatic profile of the wine. So that's why we always recommend to use tannessence volume. When you move the wine, it's going to be a great antioxidant, but it will help you controlling microbes as well. The other tool that we have on our hand as winemakers is glutathione. We know that glutathione is a great reducer. It's actually the strongest reducer we have on hand. It's stronger than sulfur in terms of lowering redox potential. It's a great antioxidant. It's a natural antioxidant that is present on grapes. The thing is, unfortunately, when we arrive to wine stage, we usually don't have any more glutathione because we have been using it with oxygen through, during the life of the wine. So during juice stage, fermentation, the yeast can consume it to produce thiols. So we have almost none arriving end of fermentation, but we need some to control microbes and redox potential and oxidation during aging. So the way to add it, or the way to increase the concentration in glutathione in wine, is to use yeast derivative rich in glutathione or sulfur peptides. In our case, our richest yeast derivative that we have for this application is called Aroma Protect. So you can see in its composition, so when we look at the sulfur peptide composition, more than half of the composition of Aroma Protect is glutathione extracted from yeast. So it's a very rich yeast derivate, very efficient to lower redox potential, so to put the microbes in a very uncomfortable situation, but also to limit dissolved oxygen and to protect the wine from microbial contamination, but also from oxidation. So it's a tool that we use to elongate wine shelf life. I'm going to show you very quickly two results here, two trials where we are looking at the amount of thiol, so the amount of aromas that are sensitive to oxidation after 3 months here in this graph. So you can see the control and the one with Aroma Protect were the same wine to start. 3 months after, The control lost most of its thiol, while Aroma Protect lost just a little bit. So the product did a great job in protecting the aromas of the wine, which means it did a great job in lowering redox potential and limiting the amount of dissolved oxygen, that limiting the oxidation reaction. Second graph, completely on your right side of the screen, you can see that this is 6 months after we are looking at how much aromas we lost from the beginning. The control lost from 55 to 75% of all its thiol compounds, while the Aroma Protect 6 months after the addition lost only 20 to 30% of the thiols. So it's a very efficient product for antioxidant, but also as a lowering redox potential. So the next point we need to talk about, this was about the wine condition and the cellar condition. The next point I want to talk about is about using antimicrobial agents. We have several available in winemaking. We can use sulfur. We all know about sulfur. We can use Lysozyme, Chitosan, DMDC, which is Velcorin, and sorbate. DMDC and sorbate are very specific to yeast, and they are having a lot of side effects and requirements. So I will not focus on DMDC and sorbate, which also are products that you use just pre-bottling, but not necessarily during aging. And today we focus about during aging. So the first one would be sulfur. Sulfur is great. Sulfur, everybody knows it, but sulfur has limits. The first limit that we are facing as winemaker is the consumer demand. More and more people want allergen-free wines, and they want less sulfur. Sulfur has been in the target of people, and it's very trendy to make wine without sulfur. So the consumer demand is asking to reduce sulfur usage. But there is also technical aspect. Sulfur acts as a solvent. It's extracted from grapes, some compounds that sometimes we don't want. It can impact all the fermentation by inactivating thiamine or by adding some stress on the yeast or some bacteria, favoring the synthesis of H2S by the yeast, other reductive aromas. It's also destroying the microbial natural equilibrium. So it's creating a microbial vacuum by destroying completely some population, but not all of them. So some are resistant, some not. And we change completely the natural equilibrium, making some strains completely dominant, such as Brettanomyces sometimes, that will be resistant to sulfur. So it's not a great tool to manage microbes. It bleaches color, it closes the wine, and it's not always effective as an antimicrobial agent because it depends on pH. The only part that is interesting in sulfur for antimicrobial effect is molecular sulfur. As you can see here, for antimicrobial effect, the bound sulfur does nothing, and in the free sulfur, only the molecular sulfur has an impact. Okay, so great antioxidant, not such a great antimicrobial effect, because molecular sulfur depends on pH. Nowadays, we have higher and higher pHs, which doesn't allow us to use sulfur as an antimicrobial agent. You can see here in the graph, I just gave you an example. If we are talking about a red wine, 3.8 pH, which is high, but not crazy high, we would need 80 milligram per liter of free sulfur to be covered as antimicrobial, which is pretty much not doable. The wine would smell way too strong sulfur, and it will be damaging completely the color, the structure, and the organoleptic properties of the wine. So we need alternatives. So there is other tools such as Lysozyme. Lysozyme is known since a while. It's an enzyme that is extracted from egg whites. Could actually just as that's more a general point, but it could also be extracted from when you cry, from tears, and also from breast milk. That's two other way to make it, but the most efficient way is egg white. And unfortunately, egg white is an allergenic compound, so lysozyme is not vegan and it's not allergenic. It's allergenic. It is an enzyme and it reacts only with the cell walls of the gram-positive bacteria. So it will only work with lactobacillus, pediococcus, enococcus. Okay, so great tool to avoid malolactic fermentation, but it's not gonna do anything against Brettanomyces or Acetobacter. Okay, and there is some side effects about using lysozyme in red wine. Since it's an enzyme, it's actually gonna bind with color and with tannins, reducing the color intensity and the hue, the red hue of the wine. In white and rosé, it is an unstable protein, so it requires to use more bentonite to stabilize the wine, and usually you can't use CMC when you use a lysozyme without using a lot of bentonite. Okay, so a great tool for gram-positive bacteria, but also a lot of side effects. So the other option that we have is Chitosan or Chitosan. Chitosan is the newest antimicrobial agent that we have in wine. It is derived from Aspergillus niger, so it is vegan, it is allergen-free, biodegradable, and it's a fining agent. So it's not staying in the wine. It has a wide spectrum antimicrobial activities. So Chitosan will work against Lactobacillus, Pediococcus, Enococcus as lysozyme, but also Acetobacter and Brettanomyces. So in one treatment, you can do basically all the microbes that are dangerous during aging. How it works? The first thing is a charge attraction. So you have the Chitosan and the cells that are going to be attracted because they are opposite charge. The Chitosan is positive, the cell walls are usually negatively charged. They are attracted, as you can see here on the picture. We just make like a big mass of cells and Chitosan. Then there is, at this point, there is an alteration of the cell metabolism because basically the cell can't breathe anymore, can't communicate with outside. The Chitosan is all around there, and also can't feed. There is no food intake, and so there is no more metabolism happening or an alteration to it, which means we will have less spoilage, less contamination in terms of aromas. Then the next step is a perforation of the cytoplasmic membrane. As you can see here in the cells, so here it's actually 5 minutes after the Chitosan treatment, so it's very quick, the action of Chitosan. There is a perforation of the membrane, and the leakage of the cell. You see here you have before treatment, and here you have after treatment, and you can see that the cell is emptying from the inside. So as soon as there is leakage, there is death of the cell. Here is another way that you can see it. The first picture that you see where my cursor is a wine without treatment. Second is 1 day after Chitosan, already the cells are leaking. There is no more perfect membrane, and there is some pieces of cells that you can see here outside the cells. 4 days after, some cells are completely disintegrated, and this is 8 days after, and there is basically no more cells. Everything is disintegrated. The last action of Chitosan is settling. So it's gonna bind the cell, it's altering the metabolism, it's opening, perforating the cytoplasmic membrane, leakage of the cells disintegrate completely, and all these pieces of cells will be falling down the lees with the Chitosan. Okay, so how do you do it in a more practical way in the cellar? You would use products such as KILLBRETT. KILLBRETT is Lamotabier Chitosan. It is 100% Chitosan. So if you compare to other Chitosan, what we are doing is we are using way lower dosage of treatment. For KILLBRETT, we are talking from 4 to 8 grams per hectoliters. Very low dosage. So we have a limited impact on organoleptic profile, and we have a limited loss because our finding is actually very small. It is a product that is fully TTB approved for domestic and export. Okay, so we're covered on this. As you can see here in the picture, we have a control here with, so it's Brettanomyces plates. So we have Brettanomyces cells in the control, as you can see, with 4 grams per hectoliters. We already don't have them. We have none. And with 8 grams per hectoliters, we have none. So very efficient product, even at low dosage. In a preventive way, we use 2 to 4 grams per hectoliters, depending how risky is the wine and depending the conditions, all the other conditions we talked about before of the wines. And we realized after some trials that the protection is actually maintained for about 4 months. This can be used on white, on red, on rosé, on sparkling, on any wine. And again, KILLBRETT is not only for Brett, but it's also efficient against Lactobacillus, Pediococcus, Enococcus, and Acetobacter. Curative means you know you have a population in your wine, you know you have a contamination, you need to get rid of it. You will add 6 to 8 grams per hectoliters to your wine. You will let it settle for a few days, about a week. You're gonna then do a racking from the lees, and then we recommend to use 2 grams per hectoliters as protection, and you leave it in. So when it's preventive, protective, you leave it in, no need of a racking. When it's curative and we go higher in dosage, we recommend to do a racking of the lees. Okay, so what I would like to do is to show you some trial results, because I can talk about it, but we actually have a lot of data to show. So I'm very happy to be able to show you some data and some well, a way that you can be a little bit more convinced, maybe. So here trial results on Brettanomyces. So we are talking about a Cabernet Sauvignon, about 14 of alcohol, 3.7 of pH. We are looking here at 2 different things. We are looking at the impact of stirring and the impact of KILLBRETT. So we have a wine with sulfur. As you can see, we are at 37 free sulfur here, and the same wine that we are stirring. You can see that when we stir, we are increasing the Brett populations because we are putting them in suspension, and we are also increasing the ethyl phenol, so the spoilage of the wine, because we probably introduced oxygen, we put in suspension some nutrients, some substrates for the Brett, and also we put them more active. Okay, so stirring here is actually not a good idea to limit spoilage and microbial contamination. Here we are having no sulfur but KILLBRETT, and when you see, with the KILLBRETT, we are actually completely removing the population, no more Brett. We removed some methyl phenol too, so we are way lower than any detection threshold. And when we stir with KILLBRETT, we still find some Brett, but in a very low population, like the control, basically. But we don't have ethyl phenol, so we found population of Brett, but we didn't find volatile phenol, which means the population we found are not active, are stick to the Chitosan, and they are actually not producing any volatile phenol, so they are not dangerous, they are not at risk. So KILLBRETT is very efficient in removing Brettanomyces cells and preventing the production of aromas. Also, stirring heavy lees will result in higher contamination and higher risk of spoilage. And we actually have further trials that show that this effect can last about 4 months. So that's what I was telling you previously. Another trial here where we are comparing KILLBRETT versus 0 sulfur versus 0 sulfur and 30 milligram per liter of free sulfur versus 0 sulfur versus 0 sulfur plus 4 gram per hectoliters of KILLBRETT as preventive. This trial has been done in many replicates in actually 2 different wineries, and these are both on Pinot Noir, and it's a summary of the results. So we did all of this is winery trials. We looked at the color because that's something also interesting. So of course we reduced sulfur since we didn't put any, while the other one was maintained at 30 ppm of free. When we look at the color intensity, we can see that the KILLBRETT has the highest color intensity. The wine in blue is the wine with no sulfur, so KILLBRETT is yellow. The wine in blue with no sulfur has a little bit lower color intensity, but still very close to the KILLBRETT. The wine with sulfur in purple here has a lot less color intensity, and that's the bleaching effect of the sulfur. If we look at the variation, so this is from January to November, so we almost have a full year of data. In 1 year of aging, with no sulfur, we lost 10% of the full color. With sulfur addition, we lost 25% of the color, and with KILLBRETT, we lost only 5% of the color. So great tool to manage color too during aging. If we look at the color variation in terms of hue, so here we are looking at the C-Lab method. So the A is showing the red color, the red intensity. The B is showing the yellow. Okay, so as you can see here, with the sulfur, no sulfur, we lost 5% of our red and we gained 30% yellow because we got oxidation. With sulfur, we lost about 8% of the red and we gained 26% of yellow because we bleach, and so we change the hue into more brown yellow. And there is some oxidation too. With KILLBRETT, we actually gain 11% of red color. That's actually just a way of the visual works, and because the color got more stabilized during time. And we gain only 15% of yellow. So really our hue is completely different. The wines were completely different wines with a way better color on the KILLBRETT trial. Now, if we look at microbes, because that's what we're talking about, and it's also very interesting, here acetic acid bacteria. So you can see basically the wine without sulfur has way higher acetic acid bacteria than the wine with sulfur or the wine with KILLBRETT. The wine with sulfur and the wine with KILLBRETT are very similar in terms of acetic acid bacteria population, where we managed to control them and we are at 0. There is a peak here in June, as you can see, with the temperature increasing. To reduce this peak, we actually added some tannessence volume and aroma protect. So we added this to all the wine, which allowed us to lower redox potential and to reduce dissolved oxygen. So the acetic acid bacteria were having no nutrients, and so we managed to reduce the population naturally like this. Then we look at the VA. So here you have the evolution of the VA, which goes very much with the population of acetic acid bacteria. So the one with no sulfur has higher VA than the one with sulfur than the one with KILLBRETT. So no sulfur KILLBRETT is the best way to manage VA. And here we look at the lactic acid bacteria population. And as you can see, no sulfur with KILLBRETT or sulfur is pretty much the same way to control lactic acid bacteria, while with 0 sulfur, we maintain a pretty high population with a high risk of spoilage. Okay, so KILLBRETT is a great alternative to sulfur to control microbes. It's also a very interesting one. Now let's look at the tasting notes of these 3 wines. So the wine without sulfur was having a great color, but with evolution notes. On the nose, it was fruity, but people detected some volatile acidity, and they detected as a pickle note, but the oak was very well integrated. Then on the palate, it was actually described as a very pungent aromas, a bit burning of the VA, and then a rough finish on the palate. The wine with sulfur, so aged with 30 milligrams per liter of free sulfur all its life, was having a pale color with a way lighter wine with more brown hues. On the nose was very clean, precise, and fresh, but not very expressive. It felt like very contained and closed. On the palate was lacking roundness, was very angular, with a very hard finish, and the oak was not integrated. Then the wine with no sulfur and KILLBRETT was actually showing a very intense and deep color, especially on the red. On the nose was floral and fruity with a delicate nose. People described it as clean and fresh. And on the palate, people found mineral notes and a very balanced mouthfeel with a straightforward palate and a well-integrated oak. So this makes you understand that it is a great tool to manage microbes, but not only, also color and organoleptic purpose, organoleptic profile. So the last part of this presentation is to talk about how to reduce spoilage risk. So to reduce the risk of spoilage, of course, after having used all the good practices in the cellar, sanitation, lowering the redox potential, limiting dissolved oxygen, and using antimicrobial agents, we also want to work on reducing substrates. On the example of bread taint, because that's the one we know the most, but that's also the most common, that's how bread taint arrives. So we start from phenolic acid that are esterified in wine, and from different steps, we arrive to volatile phenol, which are the famous bread taints, horse, paint, spicy, cloves, pharmaceutical type of aromas. To arrive to this, there is different steps. And in your winemaking process, you can actually help to limit all these steps and not arrive to the volatile phenol or less. First one is that the enzyme we use, if you don't use a cinnamyl esterase free enzyme, you will produce more phenolic acid. So the cinnamyl esterase activity will take the phenolic acid esterified into a phenolic acid, okay, which is the first step in producing volatile phenol. All the enzyme we have in La Motabier, so our clarification enzyme, Nosim Clar, or our extraction enzyme for red or for white, Nosim Crush Red or Nosim Crush White, but also our aging enzyme, Vinotase Pro, are free of cinnamyl esterase activity. So this first step is not happening. The second step is the cinnamate decarboxylase. So this step is transforming phenolic acid into vinyl phenol, and this is done with Brettanomyces or some other yeast, Saccharomyces, for example, that is POF positive. POF is a gene that we call POF for phenolic off flavor. So all the yeast we have in North America from La Motabier are POF negative, so you don't have to worry about this step either. Only if you have Brettanomyces, this step will happen, but the yeast will not be favoring or helping Brett for this. And the last step, only Brettanomyces does it, and it's a vinyl phenol reductase. That if you have no breads, you are good. If you have breads that are damaged by Chitosan, you are fine. But if you have breads and you did nothing about it, you are at risk. The other thing you want to do is to avoid to give nutrients to bread. So you don't want to add any late addition of nutrients, DAP or amino acids, no dissolved oxygen, and we already talked about the temperature and everything else. I'm focusing on the DAP and amino acid because they are actually the substrates and the precursors of other aromas, especially from bacteria. So mousiness, for example, that is mostly produced by lactobacillus. The precursors of the substrate for this are lysine and ethanol. So limiting the amount of amino acid later down the road or residual amino acid will help you limit the risk of mousiness. Same with biogenic amines, cadaverine, putrescine, histamine, all these biogenic amines that are associated with very, very bad aromas, such as dead bodies, algae, but also the flakes that you can give to goldfish in aquarium. They come from the enzymatic decarboxylation of amino acids, and this mostly from lactobacillus again. So you can avoid to have lactobacillus, but you can also prevent to give too much substrate to them. Diacetyl, these are any lactic acid bacteria can produce diacetyl from citric acid. So just make sure you don't add citric acid in a wine that is not stable in terms of bacteria. Geranium taint, if you want to avoid geranium taint, don't add sorbate or sorbic acid in a wine that contains active and viable bacteria. Okay, so basically to summarize all this presentation today and to basically give you tools as a winemaker, what can you do to control microbes during aging? Of course, the first step is really to control your cellar environment, lower your temperature, make sure you are sanitizing everything you can, make sure you are not aging your wine in very heavy lees, but try to reduce the turbidity of the wines. And then you can use KILLBRETT as an anti-microbial agent. This is covering all the palette of microbes that can develop during aging, or the main one. And in preventive, we're talking 2 to 4 grams per hectoliters with nothing else to do. In curative, 6 to 8 grams per hectoliters, followed by a racking. You can use sulfur, and we do have sulfur. We have effervescent tablet of sulfur of 2 and 5 grams. Feel free to ask me if you need help in dosage, but they are very practical and easy to use. We are recommending to use Tannescen's volume. This is to scavenge oxygen and oxygen radicals and lowering or stabilizing redox potential, which will help you controlling microbes, as you saw in the graph with acetic acid bacteria. And aroma protect, again, to help you lowering your redox potential and protecting your wine from oxidation. So with these 4 tools, you will be fully covered. You can add all these post-malolactic in your barrel after a racking, and once your wine is stopped, you are pretty much set. You know, you want to leave your wine age, but that's pretty much all you have to do at this point before, of course, you arrive to the blending, stabilization, and bottling. So the take-home message here are to manage your environment, cellar and wine, with temperature, pH, fining, reducing turbidity, removing the gross lees, lower your redox potential with Aroma Protect and Tannescen's volume, limit your dissolved oxygen with Aroma Protect and Tannescen's volume. Reduce the amount of substrate you give to your microbes, so adapt your winemaking practices and choose carefully the product you use during the process, such as your enzyme or your yeast can have actually a pretty big impact in how much substrate you have on your wine later. And to remove microbes, of course, you can use sulfur and lysozyme, but the best tool we have now is Chitosan. So KILLBRETT is vegan, allergen-free, and it works on every microbes we have to worry about. So thank you very much.